think I can use this one.
Let's just stay here.
Yeah.
That's 0 files?
Yeah.
Okay,
This
so
is-
wait na kayo.
I will try it.
Okay.
What is the pointer? Do you have a pointer?
No, we don't have a pointer.
Oh,
here.
this one, this one.
Okay.
Okay.
Okay, yeah. That's your file, son? That's your first file?
Yes.
The
Yes.
second is workshop
Yeah.
file.
Yeah. I think this one is better. Yeah. نبدأ دكتور. Yeah. بسم الله والصلاة والسلام على رسول الله. السلام عليكم. First of all, I would like to thank you for having us, me and Dr. Hadi, and we are so privileged so that we can have our talk and expand our idea about energy warehouse. So thank you all. So our new concept, we started it like 3 years ago, me and Dr. Hadi, when the King has announced about a new project. We thought about what we called energy warehouse. Can I أحتاج show it here يعني. The presentation, yeah, if that's possible. When we started, me and Dr. Hadi, so we focus in an energy warehouse in some specific location. السلام ورحمة الله.
Just أعملكم presentation صغير عشان الناس تعرف عليكم.
Okay.
Excuse me. يلا الله يعطيك العافية. السلام عليكم ورحمة الله وبركاته. Good morning everyone. So we are today honored by the presence of two researchers coming from the University of Tabuk, Dr. Hani Al-Biloui and Professor Hadi Agoon. I will give a short biography for both of them. So first of all, welcome to Hail, welcome to this big event. We are really very honored by your presence. Dr. Hani Al-Biloui is the head of the Electrical Engineering Department from the Faculty of Engineering, and he is the director of the Renewable Energy and Energy Efficiency Center in the University of Tabuk. He has received his BSc degree in electrical engineering from King Abdulaziz University in Jeddah, Saudi Arabia in 2008. The MS degree in automatic control system engineering from the University of Sheffield, UK in 2011, and the PhD degree from the Clemson University from USA. He is a faculty member at the Department of Electrical Engineering, Faculty of Engineering, and Director of Renewable Energy and Energy Efficiency Center at Tabuk University. His research interests include renewable energy, energy management, energy storage, power system quality, power system planning and operation, and power system control. Welcome, Dr. Hani.
Thank you so much.
Thank you so very much for your presence.
Yeah, sure.
Dr. Hadi Agoon He is the faculty member at the Faculty of Engineering, Director of the Sensor Network and Cellular System Research Center at the University of Tabuk. Professor Hadi received his MS degree and PhD degrees in electrical engineering from the University of Washington, Seattle. He is a life senior member in ICAAID and a professional engineer registered in the state of Washington. He served at a number of universities in the US and aboard at many academic ranks, including Edward Chair Professor. A lab he directed won the Boeing Supplier Excellence Award. He was the winner of the IEEE Professor of the Year Award, UW branch. He is listed as an inventor in several patents. He was one of the editor of books entitled Sensor Network and Sustainable Development. He served as associate editor for special issues by IEEE Access and Sensors. He co-authored many papers in IEEE and other journal and conference proceedings. He is currently professor and director of the Sensor Network and Cellular System Research Center in University of Tabuk. His research interests include power and energy wireless communication, wireless sensor networks, neurocomputing, and scientific visualization. The workshop that will be presented by Dr. Hani and Professor Hadi is entitled The Energy Warehouse Concept and Energy Management. So, Dr. Hani, welcome to HAD again, and go ahead. Thank you so much.
Thanks so much. So our presentation and workshop will talk about energy warehouse, as I told before. So this idea, we try, me and Dr. Hadi, to expand it more and to see the differences between it and microgrid and virtual power plant. So, and we hope we can deliver that to you. And presentation, just can I show the presentation here? So our presentation will have a brief introduction, and we'll talk about the new mega project and the energy warehouse implementation, the energy management system within the energy warehouse, and its operation mode and scenarios. At the end, we'll conclude and put our future work. So, as you know, there is a global acknowledgement for greenhouses effect and resulting in global warming. Countries around the area establishing plans to reduce carbon emission by adopting a green sustainable form of energy. Furthermore, there is also a parallel global race between the countries for creating free economic zones within countries to attract businesses and investment to diversify their economics and move away from fossil fuel. In Yum, as you know, I think most of us heard of it. So with its mega project in Yum, our country, Saudi Arabia, is planning to enter the race in major ways. So one of these ways is renewable energy. So Yum is planning to be fully sustainable regarding using renewable energy and even for environmental purposes. With that vast land in Yum, we're talking about more than 26,000 kilometers square city and bordering three regions, three countries, which is Saudi Arabia, Egypt, and Jordan, with unparalleled capacity of solar and wind energy. Yum, or it is invention that Yum will heavily rely on renewable. Thus, it is conceivable that it will be formed of a cluster of microgrids and distribution renewable energy sources. As we can see, in Yum city, bordering the three countries, Jordan, Saudi Arabia, and Egypt, and there is a chance even for interconnection between these countries. We know that there is an ongoing project to be interconnected with Egypt, and like last year or 2 years ago, the Saudi electricity company has signed a contract to even interconnect with Jordan as well. What is energy warehouse? So the main renewable energy source used today include solar and wind, to lesser extent biomass, as you know. These sources are stochastic in nature, and the amount of energy they produce is not entirely controllable, which result in difficulty maintaining them and balancing between generation and demand in the power grid. Recent technologies, advances in smart grid, microgrid, virtual power plant, energy hubs, and energy interconnection offers a wide range of placeable solution to their problem. Such advances have motivated the development of complementary energy warehouse technology. So in its simplest form, the energy warehouse is controlled and managed heterogeneous, massive modular energy storage and wheeling system. So the energy warehouse is not like, we're not talking about only battery storage or one kind of like a storage. So it's a combination of multi-storage. It can be thermal, it can be hydro, it can be like chemical, it can be mechanical, all within the microgrid. And these, the energy warehouse as entity itself can be interconnected between, as you can see, microgrid or multiple microgrid and bulk power system or multiple power system. As I said, so the energy warehouse will provide the link between microgrid on the other hand and the bulk power system on the other hand as well. A proper size and location for energy warehouse promises a significant technical and economic benefit. Benefit will include leveling and energy time shifting, as well as the potential to eliminate typical transmission infrastructure in certain situations, thereby reducing losses, mitigating congestion, and increasing efficiency. This table shows the differences between microgrids and virtual power plant and our concept of energy warehouse in structure, in energy management. Also it shows the similarities and differences and the preferred usage. And the main thing that we see and we believe is the different is the energy warehouse, its capability to store and wheel power as well. Is not only for storing, even just like wheeling power from bulk power system to microgrid and vice versa. As we said, the energy warehouse has several electrical energy storages modules, each of which has a storage device, power conversion units, and control system. The modulars are chosen so that they are heterogeneous in terms of their basic characteristic. As I said, it can be electrical, it can be mechanical, it can be thermal, it can be hydro, any type of storage system. The power conversion is responsible for converting the power from AC to DC and vice versa. Also, the control system controls the flow of energy into and out of the storage devices. So they're gonna be a transfer even within the energy warehouse itself. Maybe I can, instead of discharging like the storage, like the battery storage, I can discharge from the hydro. What is, it's based on like economic benefit, the rate of discharge, and another constraints. So we can do transfer within the energy warehouse. Also, we can do the transfer between energy warehouse, bulk power system, energy warehouse, microgrid, or even just wheeling without charging or discharging. The energy warehouse also has switches that are used to route power in both directions, as I said, And for management purposes, the energy warehouse includes modules for energy forecasting, supervision, control, and optimization. So we can do like multiple optimization. It can be our cost function only focus for economic benefit for energy warehouse, or for energy balancing between energy warehouse and microgrid and bulk power system. So it can be like a multi-optimization problem as well. As you can see, this figure shows the energy warehouse architecture. The box in green represent each modules in the energy warehouse of a storage device. As I said, it can interact with each other. So we can have internal transfer, and then we can have external transfer as well between the microgrid or multiple microgrid or multiple bulk power system. If for implementation of energy warehouse, a feasible study of energy warehouse might include parameters such as sites and physical layout is very important. Energy storage device, when we're talking about the efficiency, the rate of charge, the rate of discharge, the state of charge, all these things. The storage capacity, it comes also as well. The power level, the voltage level, the number of microgrids, of type of microgrid to be served, bulk power system to be connected, switching technology, topology, environmental information such as location and climate change, energy pricing when we talk about in terms of energy market, pertaining laws and regulation. Energy warehouse as a management system. So the input of the input to energy management system of energy warehouse include but not limited to, like for example, forecast power of energy warehouse, power of microgrid, power of bulk, state of charge, operating limits, security and reliability constraints, interconnection with microgrid and bulk power system, and energy price schedule. With this input, energy management system for energy warehouse perform a multi-stage optimization to determine the optimal unit commitment and dispatch of energy storage devices according to a composite cost function. Output of the energy management system for energy warehouse will be the power cell and the power to pages, their schedules and timelines, and their prices and fees. This information is communicated to an energy market arbiter to enter the bidding contest. This is where we started to imagine it as energy market for the energy warehouse. When we talk about mood and scenarios of energy warehouse, actually we have two basic mode of operation. Energy exchange with microgrids in order to assist them in balancing their generation and demand when we talk about the microgrid side. Also, we can do energy exchange with bulk power systems in order to achieve economic benefit. I show here like many scenarios, like not many scenarios, we can imagine many scenarios, but I show here only 4 scenarios. For example, operation scenario with energy warehouse sell power to microgrid, and energy warehouse buy power from microgrid, and also when energy warehouse retain power to bulk power system. So figure 5 shows a sample energy warehouse operation scenario. If there is extra power in the energy warehouse, they can sell it to microgrid. If they need to charge their storage devices, they can buy it from microgrid or even from bulk power system. If the microgrid, if the energy warehouse, for example, if there is extra power from microgrid and that exceed the capacity of the energy warehouse, they can charge up to their limit, and the extra one can be delivered to bulk power system, or like it will be like a plenty phase for the energy warehouse, because we need to make sure every time when we do the optimization, everything is balanced. Also, we introduce the bankruptcy problem. Usually, this bankruptcy problem, you see it in economics. So we introduce it to our energy warehouse, assuming E represents the amount of power or energy in the energy warehouse. There will be two exist possibilities, which is called in economic background the single assist model or the mini assist model. The single assist model, this is the case where the energy warehouse is debitor and the microgrid are a creditor. This is what we considered for our introduction of energy warehouse to bankruptcy. So bankruptcy problem means, so let's imagine if you have a bank and you are bankrupted, and how can you be just and fair to distribute what you have among your client? So this is how we think about it. Let's say energy warehouse has a certain amount of energy, and microgrid, they need like multiple microgrid and bulk power system need this power, which is exceed our limits. So how can you be fair and justice? So in our example here, we assumed we're gonna have like a 3 microgrid. The multi-grid one, it's shortage for 1.1 per unit, microgrid 2, shortage 0.2, microgrid 0.4, and what we have is 0.6, exactly as the shortage. How can I be fair between to microgrids? So shall I give it like 0.4 for microgrid 3 or 0.2 or 0.1? So we apply different methods. So table 1 showed the Shapley value method. The first column shows the ordering, how you can deal with each one, how you distribute the 6 per unit in energy warehouse among the microgrids. And also we applied different method. Table 2 shows the solution of the bankruptcy problem in energy warehouse, the Shapley value, as you can see, and the proportional principle and the consistent agreement principle as well. The concept of energy warehouse and energy management system of energy warehouse provide a feasible solution to address the new objective, which is, as we know, all of us, I believe, is totally green. With the current interest and investment in development of wind and solar, as well as other technologies such as those based on pumped storage and biomass, there is a potential for the success for energy warehouse concept. Also, our future work that will include how to reformulate energy management system applications such as unit commitment, and economic dispatch, and establish effective control schemes to regulate voltage and frequency for the highly heterogeneous energy storage system within the energy warehouse. What form will be the business contract take for wheeling the power between energy warehouse, bulk power system, and microgrid in order to ensure secure and reliable operation while maintaining the rule that energy warehouse is designed for? I think that's it all. I'm happy to have any question for you, and if you have any question.
Thank you. Maybe to postpone the
that's
discussion.
fine.
Yes. Okay, so we will questions after finishing this workshop. So this is the first part. Now I am pleased to invite Professor Hadi Agoon for the second part of this presentation. Professor Hadi, please come on.
Thank you very much. If you can show presentation, Dr. Hadi presentation here.
الفائل الثاني نتكلم الاي تي.
Dr. you can go this one and this one as well. Do you need this one? You can scroll here, you can scroll here as well. See the screen?
Okay, so just scroll up. This is up. This
No,
is
no,
up.
no, this is up, this is down.
No.
This is to control that screen. And to control
Okay,
the screen here
okay,
from
good,
the left.
good. Okay, thank you very much for having me again, because I was here before. So thank you so much. Just to give you a little bit of a background, as Dr. Hani mentioned, this idea is new. Actually, when we saw the event here, we didn't have per se material to present, but when we talked to Dr. Hussam, then we really were like upfront. We have applied for a patent actually for this concept, and it with the US patent office, it's in second year. So when Dr. Hussam invited us, we just had to really, like say it, and nothing, we hide a little bit, but not that much. This is in the spirit of sharing knowledge, okay? We're very happy because it's our creation from the bottom up. But as we went and started thinking about it, many issues came about. Some of the operation was technical. We're good at that. I mean, optimization and all that stuff. But soon we encountered other areas that we really have to be, to be aware of. Business. And thus the issue of, for example, of bankruptcy and how, for example, the warehouse divides whatever it has power to satisfy on one hand microgrids attached to it, and on the other hand acquire the power and store it at a minimum cost to distribute it, at a reasonable and humanly cost. So it was a multifaceted problem that took our journey from our typical engineering to AI applications, for example, for optimizations and knowledge management, to business and obscure actually business concepts that you don't see every day in academia. Having said that, we organized this like a workshop, like a typical workshop where people, for example, gather in groups and we do this. But we don't have to do that. So we're just gonna go linearly through it. And what we hope at the end of the day is you have questions or you pick up on something, a new area of research. It could be a good area for somebody, it could be a good thesis for a student, it could be anything that you can think of. And furthermore, I mean, we're a sister university after all, especially with our last relationship. You probably know what I mean. We will be open to share information, to disclose information, and hopefully once the information goes to you, we learn from it again and evolve. So when you look at the energy warehouse, in the work we have done, we basically focused on 4 scenarios, because this is one of the technologies that works with scenarios. What if this, then we have that. What if those 2 things happen, and how can we deal with a situation that we haven't seen before, how to go about that, okay? So basically, it lends itself to a type of technology that we'll talk about. So having seen, for example, some of the scenarios here, the ones that are, 1, 2, 3, 4, for example, the energy warehouse can satisfy the demands of the microgrids and everything is good. Then, it could happen that in number 2, that the microgrid has excess power. And so what happens if the microgrid has excess power? If it leaves it like that, what means is the frequency within the microgrid will goes up, and that's a no-no. Okay, the frequency has to be just 60 hertz if it is 60 hertz. Can you put back the? Okay. So in other words, at times, the energy it's almost like a phoenix. It can provide the power to address issues within the microgrid, like frequency fluctuations and all that stuff, peak shaving. How about if the energy warehouse doesn't have enough room in its modules to store it? Because the energy warehouse just stores. It's like a warehouse. It stores. It doesn't create. It doesn't absorb. So what does it do with it? Okay, so here when it's like you have a contract with somebody, and if you don't do what you agreed about, you have to pay a penalty. In other words, the energy warehouse might, in some cases, dump energy and pay for it. If you can imagine that concept, please. Okay. So we in literature we went through many scenarios, but here, for example, you can ask yourself, okay, are these really all the scenarios that the energy can have or can handle? Okay, what other scenarios? And you may find, for example, sorry, let's see here. I didn't mean that because I thought it was a pointer. So I need to go like this, yeah. This way. Nope. So now I told you everything. Okay, let me go back. No, it's not that. That's not what. Can we put it back? Yeah. Okay. I just wanna go to where I was. Exactly.
It's okay. Go ahead.
Here. I was here.
Okay.
So somehow when I go down, it still go up. So I go back. So where is? Yeah, 2. Yeah, I hit up. Anyway, it was. Yeah. Maybe you're luckier.
Why don't you use this one?
Is it?
Yeah, you can.
Oh, okay. So this is. Yeah, but I don't see it here.
No, don't worry. Just look here. I'll command this one.
Okay. Go ahead. Yeah. All right. Thank Dr. Hen. This is why you have Department Arabic direction and English direction, probably. Okay, can you go? Okay, I see. Okay, I got it. Now up and down, clear. Okay, so anyway, the question here, once you see all this model and all these things, just ask yourself what other scenarios that might be. Here we suggested 2 scenarios. Okay, you have a VM here, so you can okay, that will give you a new area of work. The other thing is in terms of energy management. Now, in the energy warehouse, there are many modules that store power. Okay, so these modules store power at different costs. okay, because one of them could be just batteries, the other one could be a hydrogen-based storage system, and the third one could be even some of those new technologies based on like those mechanical weights or tracks for mechanical systems for storing energy. So each one stores energy at a different price. How, when you get to store your energy, how to choose the appropriate one? So because you're to, it has to make a benefit. So if you don't choose appropriately the modules, you're not going to realize the benefit into unit commitment. Here, you're talking about energy storage. Okay, so does that change the picture? Okay. So then the idea will be thinking about it in terms of like a system point of view. So in other words, so you have a schedule for your Egypt and Saudi. I need it. And then you have the technical parameters of the modules in terms of their capacity, in terms of, and so on and so forth. And then you have the cost of the storage, and then the availability schedules. It takes you totally. And I'm talking in the sense of systems. Okay, decision function. Okay, the decision function, which I call F, which really depends on vectors. On vectors, like for example, the power scheduled. Okay, the actual power between the energy warehouse and on one hand energy the microgrids and the bulk power. The cost vector, and then T, which is the time schedule. So you somehow massage this into a formulation, and at the end you should get the vector M that includes the set of modules that will be appropriate for charging in order for the warehouse to realize the gain or the benefit. Another one is really to go back and another way to really comprehend what the thing we have on hand is to go back and compare it to all the other technology that are available that can be compared to microgrids or to virtual power plants, okay? Or we can think about also comparing it to technologies such as the energy hubs. These are also existing technologies. Energy hubs that within them also they're what we call the energy interconnections. So in other words, for us to create this theory and this technology and things like that, we have to prove that brings something new, that could be, a lot of room of research, just understanding those differences and really filling gaps that might be in our coverage for the energy warehouse. Okay, that's a theme of research. The other thing is when we talk about decision functions, we cannot avoid, thinking about, especially now that the computing power is cheap. We know a lot about parallel processing. We know a lot about AI technologies, deep learning and all that stuff. So you could, and since the warehouse lends itself to scenarios, then that begs for a knowledge system, okay, for storing those, and then another way also to really get something to work on when it comes to the energy warehouse is just ask yourself, and since this is a I'm sure you will find a lot of questions that are not answered by us for sure, because we haven't really looked at everything. And you can start like this, you know, does EW produce power or energy? At this point, no, because that's one way to make it different than other technologies. For example, you take any question. For example, can the EW modules be energy hubs? Or can the energy warehouse itself be part of a virtual power plant? Okay, those questions are very legitimate, and they could be also an enabler or a room for further research. Here, when we talk about the energy modules, a lot of people think, you know, you're talking about batteries. We're not talking about batteries. We're talking about a heterogeneous system, as Dr. Hani said, which include different types of energy storage, from hydrogen to batteries to others, to new technologies, such as the lower one, you know, blocks and cranes, if you know that, you know. At times where energy price is low, you take like weights up and leave them up, and when you need energy, you let the weights go down and you generate power. That's one way, and this also cited in one of NUM documents as being, you know, a possible technology in NUM. The other one above is we call it chains and tracks. In other words, you put weights on chains and take them up when energy is down, and you let them scroll down with those weights and generate electricity when it's time to generate power. So these are what's inside, you know, the typical things that are inside the energy warehouse, the modules. And thank you very much.
Thank you so much, Professor Hadi.
Thank you so much.
Just we will start by some questions. Me, myself, I have many questions. Dr. Hani, please come on stage. We will ask you about this very interesting presentation. So any question, please?
Assalamu alaikum. Thank you for this nice presentation and very informative presentation. I came late, but I'm trying to ask one question because you are talking about the objective function or the cost function, and there are a lot of parameters inside. So is the value of the parameters is the same? Maybe you have to put some weight factor there inside. So one parameter is has a high impact, the other one has less impact, and in this case, we need to have some factors inside to make the difference between each one. The other thing is, what are the constants that we should consider when we are taking account about this cost function? And the main thing, can this cost function change in real time? Because maybe the next week it will be not the same, the other week it will not be the same, and so on. So what is your opinion about this? Thank you.
I think the first about the question, the first question you're talking about, what are the main constraints when we do transaction within. I think it has to be with many factors, and we still look on it. Like for the example, the state of charge, the rate of charge, and the rate discharge of each module. Also, the efficiency is really important. So, is it good? Like, if and how can I do the interaction? Shall I use DC-DC bus, and instead of going outside the AC and go back to the DC, why I don't use DC-DC bus within my my energy warehouse modules. It has many factors. We're still looking for it, actually.
Okay, so that's what it is you're, I think, alluding to some sort of penalty factors. Exactly. Yeah, I was trying to read your mind while my colleague was answering your question. What it is, it's very legitimate. For example, when you look at the decision function, you're talking about vectors or arrays. I can even make a little bit of a shift on, take advantage of your question to even suggest something else. For example, you're given a module, okay? Certain parameters might have less importance than other parameters. And that's what you're talking about. So indeed, so this will be like a very good way to formulate this. So why don't I, since these are vectors, I can put like penalty factors and weigh them, such as you know, the weighted result will reflect better that module than that module than that module. In other words, in your optimization, that module will have a higher weight, your favorite. Yeah, I hope that answers a little bit of your question. If it didn't, then what you mean is probably a little bit more research.
Another question is because the decision function will be changed from time to time.
It
In real time.
It really does.
Yeah.
Yeah, it exactly. That's why we didn't forget that time thing. I mean, we mentioned it, but we weren't specific because it really depends on how you interpret it. You can interpret it as a matter of like unit commitment, real time, like unit commitment, where you split it hour by hour or even chunk of minutes by chunk of minutes. Yeah. So it totally true. I mean, I think you understand.
Any questions?
Assalamu alaikum wa rahmatullah.
Salam.
Sabah al-khair. Thank you so much for Professor Ihadi, and thank you so much for Dr. Hani. I would like to welcome you at the University of Hayel. I'm Abdulaziz al-Malak, Assistant Professor at the Department of Electrical Engineering, and also the Supervisor of Energy Efficiency Unit. And I guess this is part of your interest. And I guess what you have done is excellent work at the University of Tabuk, and it's been already we read about it. And I would like to thank you about the energy warehouse concept, which is, what you are proposing now is new in the field and is very informative. My question is interesting on the AI applications that you are proposing to solve the automation for this application. So how do you gonna apply it or conduct it on online application? And as you know, it's gonna be training on very big data. This is my first question. And the second question, how would you collect the incidence of the optimization parameters and costs that happen? So these are my questions. Thanks.
Yeah, I will. Okay. No, that's fine. Come here, Dr.
Yeah, I mean, I will only dare to suggest, a couple of things. They may not be the exact answers. But in terms of AI, when you look at the structure of the energy warehouse, the main components are really inside, are those modules, and how to deal with them, okay? How to choose them, how to choose And when I see a problem like this, and because we were thinking about it even before, I can't, and I have a background in communication, actually. That's, you know. So in communications, you know, we use concepts like ensemble learning, especially in neurocomputing. So in this case, it seems like that concept would apply to this, because what it is you're talking about basically a modular network, or a modular network. So each module is actually a neural network. This is if we're concerned with neural networks. And then each one can be targeted to one of those modules, okay, with parameters as input and parameters as output. And then you have the classical technologies within AI to choose which module will be prevalent at one time, okay? So the training will be a lot easier because you're training, you're talking about training, you're training with homogeneous data. In other words, one module will just be for example, one of the storage technologies. So you expect it to be homogeneous. The other one will be totally different than that, but within that neural network, they're homogeneous. So in other words, you know, you can play it like that to have a really a nice, or at least theoretically, a nice overall neural network, an ensemble network that would give you the ultimate, the overall decision. Okay. So that's the, in other words, I'm not saying this is the answer to your question, but that's one way to think. Your other question is with regard to, maybe Dr. Hani will be able to.
I think I will add, I have the mic. Also, as I said before, energy warehouse can be multi-optimization problem is based what do you want to do. So you can do the optimization just within the energy warehouse to figure out how you to interact between, instead, as I said, if discharging from the system, no, as an efficiency factor, I can discharge from like the battery storage or from the hydro. If you expand your optimization to include the other entity like bulk power system and microgrid, I think the most important thing is to rely in the sun and wind data on the microgrid side, and on the bulk power system side, you can focus in the load profile. So you can have their load profile. You can predict, use like AI techniques to predict the load profile, and then you can do like one of the big optimization problem or multi-stage optimization problem.
I would like to add one thing to what Dr. Hani said, which really goes back to those penalty factors. Now, we talked about those penalty factors within the parameters of a module, but when you formulate cost functions, you can also revive those penalty factors. For example, you want to maximize the gain of energy warehouse, but remember that you can either have power coming from the bulk power systems or going to them, and power coming from the microgrids or going to them. So each one type of power within the warehouse, outside going to the bulk power system or to the microgrids, these could have penalty factors in terms of certain costs, you know, that weighs one against the other one. Hopefully the answer is somewhere in this.
Any other question, please? Okay, so
Thank you. Thank you so much.
It's time for me to ask you.
Yeah.
I will monopolize the antenna for a while. Okay. Yes, of course. As a first glance, I was really confused when talking about energy warehouse. I suppose like I'm in front of a system of energy storage, but when looking for this very inspiring presentation, I'm aware now that it is a big block with control system, with energy management. So we are in face of, like you said, of a stochastic system in terms of sources of energies and scenarios, okay? And logically talking, we have to go to optimization, we have to go to artificial intelligence and so on, okay? What I can say that using these techniques, there will be, whatever the performance you will reach, there will be a term of error, okay? Behind there is a big security and safety questions. So the term of error, how much does it impact these issues in terms of safety and security, and any research is leading over that?
Again, it's like when we started speaking, and every time there is an event like this, we ourselves discover things and discover new questions. So when you say security, is it in terms of post-mortem security, like we know in power, with the Diliaco model, normal, alert, emergency, extremis, restoration, all that, or the security in terms of computer security and things like that?
I'm talking about the process itself.
So you're talking about basically the classic definition of security. It is a system. You go back to the definition of the warehouse. It's really a system that wields power and store it for short times. The security I can define here would be, for example, within the warehouse, whether, for example, monitoring the voltage, for example, in certain nodes or buses, like are they within limits? The power flow between modules, is it within the thermal limit of the carriers? And if there is such a thing as frequency within the warehouse. For example, if you're talking about those things, it depends on how you design the powerhouse. Is it, the warehouse, will it be based like a DC? Yeah. Will it be like a DC technology or AC or a mix? And this we really haven't even come close. Right now, in our meeting of last week, we were just talking about what would be the most appropriate. Will it be DC or AC within the structure of the warehouse? So we haven't reached that stage yet. I mean, but in terms of security as a concept, yes. I mean, you have to face it. You have to face it with what we call the Diliaco model, which is like I described it, the cycle of normal, alert, emergency, extremis, restorative to normal, or that has to be, so that you take the energy warehouse and you look at it within this concept and see how you apply it, okay? And there is also the other issue is you have a lot of modules, and you can also think about the other type of security, which is hacking and impeding the operation itself of the energy warehouse. That also an aspect that needs to be considered. So these are the two types of security I'm aware of, and we're no near those yet. It is something that we hope somebody will pick up and analyze.
The system of the intelligent system, is it aware to be extended in terms of scenarios?
Oh yeah, I mean that's why we suggested a knowledge base. The extension, if I really understand you, the extension would come from adding scenarios because somebody is smarter than us and came up with scenarios and coded them, or from the normal operation of the power system, because when you operate as a user, as a user, sometimes you inquire, you make a new inquiry that become the question and the result that become also part of the knowledge base eventually. So it's like an incremental learning for the knowledge base. If you structure the knowledge system or the expert system as we design it will really have that cycle. Have that cycle of incremental learning. I don't know really if I even answered your question. We can have time and discuss that. And again, we're not saying we know everything about this, although we created it. Believe it or not. I mean, what we know for sure, because we encounter ourselves. Every time we look at it, we can see another aspect, like this, the business thing, which is the bankruptcy problem. We never thought about it until we faced those problems, and we read until we encountered the issue, and we found it to be really applicable to what we do, and we adopted it, and we had to learn it. We really didn't have anything to do with business.
Thank you very much.
Thank you so much.
Thank you very much. Any other questions?
Thank you for the this presentation, and congratulations on this invention indeed. My question about the bankruptcy framework for distributing energy. By Dr. Hani, he mentioned in case of the need for each grid, right? So, but have you considered the amount of energy generated by these microgrids? I mean, when you distribute or return the energy, which you have at the warehouse, you just mentioned, or Dr. Hani just mentioned the amount of need for each microgrid, and most of them, sorry, one or two, they don't get the needed amount, indeed, right?
Yeah.
So, but maybe this grid had generated more energy than the one more need, indeed. So, have you considered this? Because otherwise, these microgrid energy, they will start to establish their storage system, and they will disconnect it from your warehouse.
I'll add something. So when we introduced the bankruptcy, we know they use it for economics. So we imagine that maybe we have 1 microgrid, 2 microgrid, up to n numbers of microgrids. So maybe you did all the prediction, everything was perfect, but suddenly there is a problem. There is like clouds, there is something happening in the microgrid, and you cannot interact with the microgrid. There is a problem like with the bulk power system, you cannot buy or wheel. So literally, how you deal like with these microgrids? So we came up into concluding, okay, if we have only this amount of energy, and ETH entitled as a bulk power system or microgrid 1 to n, they need, how we can be just and fair. So shall I give it all just to 1 microgrid and ignore the other, or should I give it to bulk power system? So we think about the scenario. So just to give what we have. It's like, as I said, it's like you have a bank and you bankrupt it, and how you return the money to the customer. So maybe that customer, he has like a share up to like $1 million. This one has a share of to $5,000. So are you gonna give like this one the amount, like 100, the 1 million, and with the $5,000, are you gonna give him? So we're trying to be just and fair. This is actually, when we looked about bankruptcy problem in power system, we couldn't find, we find like 1 or 2 paper. They explain it very shyly. As well, we explain it very shyly. We don't like take deep investigation. But when I said bankruptcy, we thought about like, we only have this amount of storage for early sudden situations, circumstances. So this microgrid need this one and need this one. And bulk power system needs this amount, how we can deal with them.
Just to continue with one thing. When you talk about the microgrid has to balance its, the classical thing, power generated equals the power consumption plus losses. That to maintain the frequency. Okay. More power than frequency up, less power, frequency down. I mean, everything goes back. And why we focus on the frequency? Because the effect is extremely fast and global. So cases, for example, where the microgrid needs power and somehow it cannot have it from the energy warehouse, there are very limited things the microgrid could do. It could shed load. It could cut off its load. But that's unfair to the microgrid, isn't it? And that's the last thing the microgrid would like to do, is to shed load. And therefore, the whole thing depends on the contractual relationship between the microgrid and the energy warehouse. In that case, the microgrid could be willing to shed load, but with a penalty payment that will be issued by the energy warehouse. That's the kind of thinking, I will do when you were talking about, those scenarios. Is that approximately, or you mean something?
Just one issue. In the bankruptcy problem, you have clients.
Yeah.
Different amount of shares, but the share itself is the same, right?
They don't need to be the same, because one microgrid could be more deficient than the other one. Now there is an energy stored in this warehouse, right? Stored, yeah.
Generated by these microgrids.
No. The energy in the modules is bought at time of least cost from the bulk power systems, usually. This is the prevalent operation. It could buy them from the microgrids, but the prevalent operation, the normal operation of the energy warehouse, is to buy power from the bulk power system when the cost is least.
Okay, so this system is not isolated from the mini grid line. It's somehow connected.
Yeah, it's transactional.
Okay.
Transaction. Well, thank you very much for the question, because these are really the questions we get. It's just sometimes
we get it a lot because
we're not clear.
Yeah.
There's so much information, sometimes we're not clear in articulating.
I'm aware you are trying to hide something.
Yeah, well, we did our best. No, but like sincerely, like what we said at the beginning, we care about the patent because we put a lot of effort in it. But if a question comes, we're not going to hesitate to give the information, period. That's a decision, because we're academics and we value this business.
Okay, thank you so much for your attendance. Thank you so much, Dr.
Thank
Hani
you.
and Professor Hadi. Okay, just 1 second to promote the next coming workshop. It will be moderated by Professor Kuzo and his team. It will be started, inshallah, at 10:30. Now time to the coffee break. Thank you so much.
share Yeah.
How many people are in the room?
Yes.
The attendance people. How many people?
You want to see the room?
Oh, in the room.
Yeah.
In the room.
You want to have a look on the room because we will start.
No. I'm only interested. How many people are present in the room?
Not too much, about maybe 20 now. I'm expecting more people to come because we will start at 10:30.
Thank you.
Yeah. The first one, my slide. Yeah. Then the second one is Mukrani.
They will have a
presentation. I will tell you the name, so you give him the hand to speak. Okay. Okay. Now.
Is it okay?
Yes, it's okay. I think. Now you can switch all the mics. Okay. Please, the first slide for part 1. Okay. So we will start in 2 minutes. Yeah, it's okay. I think it's okay.
Professor Kuzu,
Yeah.
We shall share our slides or...
Yes, you should share slides because you are online, because we have asked for the video just in case of interruption of the connection. But as you are online, you will present your slides live.
Okay, thank you.
Yeah. Induction machines and multi-phase inverter. Induction machines. خلاص ابدا.
Already. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين. Now we start the workshop. We will be presented by Professor Kuzu Abdullah from the University of Jelfa. Induction machine, multiphase, inverter, topology, control and application. So we start by short presentation of Professor Kuzu Abdullah. Professor Kuzu Abdullah, it's a full professor from the University of Jelfa, member of the laboratory, industrial and automation and industrial diagnostics laboratory of the same university. Is the leader of several international projects. member in the National Scientific Council in Algeria. So also it's the leader of the or the collaborator of international collaborator in many international projects. So, Professor, you can start, okay?
Thank you very much. So, dear participants, dear colleagues, Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. So, maybe today we are talking about a topic, maybe for you it is known, for the others it is not known. So I will try to make it easier, and also I will try to ask our colleagues to make it more easier for you. Now, we are working with three-phase induction machine, and also we are working with single-phase and three-phase induction machines, and also synchronous machines. And also the transportation of the in power system is basically used by three phases. Have you asked the question, why exactly three phases? Why not 4? Why not 5? Why not 6? Why not 7? Why not more phases? You should ask this question. Is it better to go only for three phases, or we should go for multi-phases in power system? The same question we can ask, why we are using only a three-phase machine? Why not 4-phase machine? Why not 5-phase machine? Why not multi-phase machine? So if we are talking about multi-phase machine, what is the benefit that we are going to use this kind of machines? What are the advantages of this kind of machines? What's the difference between the conventional or the classical machines that we are using in our industry anywhere that are the most used machines? It's about 70% are induction machines. The slide, please. So this workshop will be presented in collaboration. We have presented this workshop in some conferences previously. So I will present this workshop with my colleagues, Professor Moukrani Lakhdar from University of Lagos in Algeria, Professor Gizanski, the Vice Dean in the Gdansk Technical University of Gdansk, and also Professor Moravich from Gdansk University of Technology in Poland. So they will help me for this presentation. So for me, I will make a short introduction. What is the multi-phase machine? What's the benefits? What the topologies? How we can get these machines? And many, many applications that we should look forward. We need to use multi-phase machines, and I have to convince everyone why we are using this kind of machines. So then we will go for my colleagues who will give a short introduction about all the kinds of multi-phase inverters and all topologies, all configurations that you can use. And Professor Gizanski will give some short introduction about many kinds of controls used with this kind of machines. And the last one is about the special case of machines. We are talking about the observers. Observers use it with mainly 5-phase machines, because actually we have 5-phase machines in some kind of industry. I remember when I was in Munich, University of Munich in Germany, we were working with multi-phase machine. At that time, we asked the companies to make for us multi-phase machine. It was not possible at that time. And we asked the company from Korea, they asked us for one machine with 1 kilowatt, that's $1,500 at that time, $15,000 to make these machines. But it was a dream for some researchers, that multi-phase machine, but now multi-phase machine is existing and it is used in some applications. When I'm talking about multi-phase machine, it doesn't mean that it will be odd or even. Because 6-phase machine is not exactly what we want to talk about. We are talking about odd machines like 5-phase machine, 7-phase machine, and 11-phase machine, because we are looking to 6-phase machines and 9-phase machines, just a segmentation of 3-phase machines. It is not what we want from the multi-phase machines. And also the people, when they are talking about how can the configuration of the models of the multi-phase machines, it's a great problem. So what kind For example, for our three-phase machine, we are using the Park transformation and Clark transformation. So how we can use this kind of transformation when we are talking about multi-phase systems? It's not a three-phase system, but it's multi-phase system. How can be this matrix for transformation from one model to other model? How we can get models of the machine? How we can make the modeling of the machine? What's the impact? What the equivalent circuits? What are the topology inside? How we can make the winding inside the machines? How we can make the slots inside the machines in the magnetic circuit? So this is many questions that we have to ask ourselves about that. And is there any modification in the rotor side from the three-phase machines or not? Should we keep the same configuration, the same topology, the same construction of the rotor without any modification? I will try to answer to a few of the questions as time will permit to me. I will not answer all the questions, but I try to do my best to go forward as. So firstly, I will try to mix a short introduction about my university. So this is the University of Jalfa. This is the Ruptura. This is the auditorium. It's bigger bigger than this one, of course. It's maybe like the other one. This is my state. We are here in that. And we are 300 kilometers south from the Algiers, the capital in Algeria. So this is the distance. You are welcome to come there, of course. So this is the surface. You know that Algeria is the biggest country, the largest country, not biggest, the largest country when we are talking about surface in the Arabic world and in Africa. Before it was Sudan, you know that. Yeah. And this is, you cannot imagine that this is the weather in winter in Jalfa. You know that in night you can have -15 in winter. You cannot imagine this. Yes, this is the climate in the winter. It looks like Europe. Yeah. So this is some photos from the streets. You cannot, because you have to drive, be careful there in winter. So this is some photos from Jalfa. So this is during the night. So this is some mountains in Jalfa. There is only in the world 3 mountains, one in Mexico, one in Salzburg, and one in Jalfa. It's a mountain of salt. So when you go back from this, it's strange. When you go back to this mountain from the other side, you will have a sweet water. You cannot imagine that. If you will come back, we can show these things. So this is the Rectora. So this is the University of Jalfa. We have many faculties. I will go quickly. We have many faculties. So of course, our faculty is the Faculty of Science and Technology, this one in green. And in this faculty, we have many departments. So I am a member of the electrical engineering department. So in our department, we have many majors there. We have in all the faculty about 33 majors. And the number of students in my university, about 40,000 students. In our faculty, I think around 6,000 students. So this is our laboratory. Our laboratory is chosen one of the excellence laboratory among 1,700 laboratories in Algeria. So our laboratory is selected as excellence laboratory, 20 laboratory among 1,700 laboratories in Algeria. So we are an excellence laboratory, and anyone of you want to collaborate with us for research, we are ready to do that, and we can help also young researchers for their research. So these are the groups. I'm the head of the power electronics and power quality. So the director of laboratory is here. I'm the head of the power electronics and power quality team in this laboratory. So these are some area of research in our laboratory. I will go faster. So these are the mine. Now let's go back to our machine, multi-phase machine, and specifically about the induction machine. So here we should ask some questions. What is multi-phase machine? The second question is why we should think on multi-phase machine. And the third question, why the actual power system is limited to three-phase machine, the 3 phases. Why? Can any one of you tell me why? Why not 4 phases? Why not 5 phases? Why not more phases? Why we are limited to 3 phases? We should ask this question surely, yeah.
The most efficient
If you have time later, I can make demonstration why three-phase machines is more efficient than the others. The losses is less, and the optimal value is with three-phase machines. I can make demonstration mathematically why this kind of machines are the power system is three-phase machine. Okay, but if I'm going to multi-phase machine, it was difficult in the past to think about multi-phase machine, for example, five-phase machine, because the power system is only three-phase machine. But with the speed and rapid and the great evolution of power electronics, it's possible to go to n-phases multi-phase machine, multi-phases. It's now possible now to power the machine, however the number of phases, using just with DC, AC inverters. So it becomes easy now to go for that. In the past, it was not possible because we have some limitation. Like the predictive control, it was not possible. But with the great advantage, with the great development of the microcontrol, we can make a fast calculation that we can go for the predictive control. So this is why a multi-phase machine. If we are asking, let's stop at three-phase machine. Why you are asking us to go to the five-phase machine, to seven-phase machine, to multi-phase machine? I'm talking about specific number of machines, not 6, not 9, not the multiple of 3, of course. So we should answer to this question. You should ask me why you are always talking about multi-phase machine. What is the benefit? What is the advantage if we are going to the multi-phase machine? Let me ask you one question for the protection of three-phase machines. If one phase were interruption in one phase, what will happen? In 1 minute to 3 minutes, the machine will be burned. It cannot work. The protection system, of course, it will save the machine. It will not be burned, but it will not work anymore. And imagine that you are in a process that should not stop. And imagine that you are in a process, industrial process, that it's delicate to make the maintenance immediately. So it will be a huge problem. Imagine that we are going to use a three-phase machine, small three-phase machines in the space. So it will be a problem. So we are talking about to find some machines that are more reliable. If there is interruption in one phase, the machine is still working with less power, with less torque, but it will continue working without interruption. So this is one from the main advantages. With five-phase, for example, machine, if there is interruption of one phase, there is no problem. The machine will not burn. It continues working. But what is more strange, if we have the interruption of two phases, the machine is still working. So you can imagine when we have higher number of phases. This is one thing. The other thing, let's say that we need to make our inverter smaller and smaller. We don't need to buy switches, power electronic switches that are high with high rating current. So when we have multi-phase machine, we can have some kind of segmentation of power between phases. We can have some kind of segmentation of current in between phases. So the switches uses will be less, and it will be rated, and we will have less stress around the switches. This is another thing. So imagine that we have the same power, and for the same power, how you can imagine the volume, the weight of the machine between 5-phase and 3-phase. I can tell you, 5-phase will power more power with the same volume. And this is from the other side, from one side. And what is important, when we are driving a 3-phase machine with inverter, you know that with inverter we cannot have a sine wave form. And so the motive force inside the flux in the machine, it will contain some kind of harmonics. These harmonics will create many components, and the torque developed by the machine contains a lot of ripples that make a lot of noise in the machine and constraints in the mechanical parts of the machine, and the bearings will be damaged in a short time. The lifetime of the machine itself, it will be reduced. So when we go to multi-phase machine, so the torque will have less ripples. As we increase the number of phases, the ripples, I'm talking when, of course, these machines are powered by inverters that contain some kind of harmonics in the output voltage applied to the machine. So this is a great advantage. So you can listen to, you can hear the machine, that the sound is more smooth. There is no mechanical stress in the machine inside. So this is another advantage. Of course, we are not talking about the machine if it is powered by three-phase power system that is supposed to be assigned form, which cannot be never supposed to perfect 100%. So, the slide, please. Yes. So what we should think on multi-phase machines? New possibilities resulting from the use of the multi-phase machine. Electric network is not limitation, because now power electrons give us the ability to go to many phases as we like. In the past, it was not possible, of course. But now, with power electronics, we can have this possibility because the power system is three-phase. So why the actual power system is three-phase? We have question, the efficiency will be important, and it will be optimized. So the optimized efficiency of the power system will be with three-phase. We have this demonstration of this. So this is a few history about the machine. How when it was started, the idea that we go for the multi-phase machine, the first time is about 1969, and with 5-phase electric drive with a voltage inverter, 2 kilowatt motor, what was by Word and Harrer. That this will, when we increase the number of phases, we will have reduced the ripples in the torque. This is important. This is very important because the mechanical stress of the machine will be less. And in 1980, you see, it's so recent. It was not, the idea, it was not old, as I have told you, because in the past, people thinking only about three-phase, because the power system itself is three-phase, and the power electrons at that time is limited. So now we are thinking to do more and more. So the fault-tolerant ability and reliability. So I have told you with interruption free, 1-phase, 2-phase. But maybe someone say, no, sir, with 2 phases it cannot be. Yes, it cannot be, but I'm talking 2 phases that they are not sequences. Means we have A, B, C, D. A and C, the interruption of AC, the machine is still working. But when we have A, B interruption, it will be a problem. Okay. Then until 1990, limited interest due to technical limitation. It's not so far. When we look back to the history, it's not so far. So since 1990, the development of power electronics, microelectronics, of course, and variable speed and the computers and so on allows the development of multi-phase machine. So the first advantage when we are talking about the multi-phase machine is the power split. So the power split between phases. The power is split between the phases. So low power rating switching device, as I have explained before, and we need small inverter for rated specific multi-phase machine. Now we can think about use this kind of machine, small machine in the space, because with some problems, if we have problems in one phase, we are not scared about the damage of the machine. Also, when we have some industrial process that it must continuously work, so we can use the multi-phase machine, so we cannot interrupt without interruption of the industrial process, and we can, when we finish the process, we can stop the system and make the maintenance immediately. With three-phase machine, it was not possible. It was not possible. For example, in the grinding of rocks, so it is important that we have big rocks. We should not, because we have big wheel put in this to solve this problem, but with multi-phase machine, we can, with 5-phase machine only, we can solve this problem. So reduce torque ripple. So this is because we are talking about the frequency and the magnitude of the torque, and the torque ripples could be eliminated, as well as the motor noises and efficiency will be improved, of course. So the other thing, the freedom of control is important, because the imagination of the model of the 5-phase machine, it will be contained 2 machines inside, one with the fundamental, the second one with the third harmonics. And we have 2 components, not like the 3-phase machine alpha beta frame, but we have alpha beta frame and XY frame for 5-phase machines. And if we have more, we will have more models of the machine. We can split to multi-machines. And so the freedom of the control will be larger. So the high reliability, as if we have interruption of one phase, two phases, there is no problem. So this is all the kind that we can have of faults inside. This is 5-phase machine and 5-phase inverter, you see here. And we can have many faults inside the machine, in the inverter. And so with multi-phase machine, the problem will be easier, and the faults will be easier and can be tolerated, and is more reliable. So this is just to give you a few examples. So here, this is the machine. You see here the speed. And you see here we have presented the current in phase AB, because we have 5 phases here, AB, and the torque. You see that the speed is smooth, the torque is smooth, it's changing with the change of the load. Of course, here we have let's go back. Yeah, this one. Here you see. Here, when we have some kind of loads, of course, there will be change in the torque, and also the magnitudes of the current will be changed, but the frequency will be the same because it depends on the speed here. Then let's imagine that what we have done here, A, B, C. Look at phase A. So there is no current in phase A. What does it mean? There is interruption. Can you have this imagination with 3-phase machine? In 1 minute, it will be burned, 3-phase machine. Of course, if we are not using protection for that. But with 5-phase machine, look at the current, look at the torque, look at the speed, it's smooth. The torque, we have more ripples, but it's still working. Look the rated torque, look at phase B, there is nothing happening to phase B. Now let's have imagination, we have interruption with phase A and C. What will happen? Look. So it's still working. The speed, very limited ripples, more ripples in the torque, but the machine, we can hear, of course, more noises, more mechanical contacts, but the machine still working, so without any problem. So this is one of the main advantages of using multi-phase machine that we are asking industry and people to come to use this kind of machine, especially, for example, for in the aircraft, for example, in the ships, in the industrial process, where the maintenance is very delicate, where the process we have to the process has to continue to work without interruption. So surely people will ask me, when we make the control of the inverter with 5 phases, it will be complicated. Yes, it will be complicated. For example, a 3-phase machine, when we are talking about the inverter, you have six active vectors and 2 zero vectors. You know that the combination of 3 switches, three legs of the inverter, the combination that you have 2 to the power to 3 means that 8 cases, 6 cases are active and 2 cases are 0. What about 5-phase machine? So we have 2 to the power to 5, and how much vectors we have? We have many vectors, and maybe it will be complicated it can be, it seems for you that it will be complicated, but it is not complicated. Otherwise, we can benefit from the new topology, and we have more choice to make the control, not like the 3-phase machine. So complex control system in case of control methods operating with harmonic injection, maybe, yes, commercial motors and inverters are difficult to access. We need to build the inverters, and there is maybe now no company is encouraged to build 5-phase machines and to solve this machine, to sell this machine to the public or to the industry, because they are not using this kind of machines and they don't have this kind of inverters. So let's use in industry now, but in the future we can imagine how it can be, because due to the many advantages that we have. So this is just about I will mention here. Yes. Oh, no, not this one. Sometimes maybe you don't believe me. You are free. You are free. This science, you are free. So this is just when we go to number phases. 5, 6, 9, 12, 15, infinite. So the limit will be 8.8 when we are talking about the reduction of losses. So we have to think that we have some limitation when we go to for the number of phases. We don't have to go to higher number of phases. It doesn't make sense because with this number 15, we see 12, maybe 11 there. It will be enough. But actually, we are using in the laboratory 5-phase machine, and we have experimented. And this machine was built in Gdansk University. We have made the design, and it is already running, and the experimental there is there. So, supply sequence. Can you have some imagination? For 3-phase, how many configurations we have? Star and triangle. With this one, with 5-phase machine, we have this one, and this one. So we have a new one. So we have a new free degree of freedom. Let's see what's the voltage that we can have. The first one we are talking, for example, using this kind of machines, especially synchronous machine, 5-phase machine in electrical vehicles. We need that our electrical vehicles to be faster, especially in the highway. So we need it to be faster. We need to increase the speed. The problem that we can use these topologies because we are working here in the flux weakening, if you know this term, flux weakening. What does it mean, flux weakening? The power is constant, and you know that the power is function of the torque and the speed. So we have to play like a game with these two parts. So if we increase the torque, the speed will be low. If we make the torque low, the speed will be high. And this idea can be used for the electrical vehicles. And with the change of configuration, we can make this. The other important thing when we use in electrical vehicle machine, we don't need a gearbox. We can play only with the terminals of the winding of 5-phase machines to change the degree of speed. We don't need gearbox. And this is good for the electrical vehicle machine. Some people are working there to make it. I will show some examples because the time for me is shorter. I have to pass I have to give the time for my colleagues from Poland and from Algeria to present their slides. So this is, let's have imagination. So this is the one. So we increase the voltage. We have top possibility, and we increase the voltage with what we call this pentacle. I don't know if you know this term. Pentacle, septacle, and so on. So this is special one. The third one is pentagon and pentacle. So that one is pentacle, so we can increase the voltage. When we increase the voltage is linked to the speed, and the torque is linked to the current. When we increase the speed, we increase the voltage, and then the torque will be decreased, and in this case, the current will be decreased, so it's a benefit. This is also my imagination. You cannot find it in the books for 7-phase machines. So how much configuration we have? We have more because it's number of phases plus 1 divided by 2. So we have this one. So 7 plus 1, 8 divided by 4. So we have, and you can imagine how we can go higher and higher with the speed as we change the configuration without changing the frequency like the 3-phase machine. So the control will be more easier. So you can have this kind of imagination. This, I try to make this. So you see how we can change the voltage, apply to each environment, in each winding, in each phase. And this I have to tell you just by changing the terms, without changing the frequency. So we have this, the p-pole, and with this one, people, but in the other side, you know that the 3-phase is just to change commutation between 2 phases. Here we can make the commutation between 2 phases. And with these 2 combinations, what is strange, you can have 3 poles. Means that you are dividing the speed by 3. And this in the other side. So without changing the frequency, without changing the number of poles physically, just playing with the terms of the machine, we can change the speed. This is why we can go that we don't need gearbox in the electrical vehicles using these kinds of machines. So this is just some configuration. This is how we can change the poles. I will get. This is when we increase the number of, this is the general case, when the number of phases. So we can have multiple levels of speeds, and this we can more and more phases, more and more speeds, and we don't need the gearbox especially in electrical vehicles. So this is some application. I have more slides. I will stop here. This is some application: traction drive, hybrid vehicles, full electric vehicles, ship propulsion drivers, electrical drivers in airplanes, because due to the reliability, if we have problem in one phase and television in one phase, we don't have problem, not like the three-phase machines. So we have many applications. So we need this. We need to have this in electrical vehicles. This is an important thing that we need to have in the electrical machines. So with five-phase machine, we can benefit and we can achieve this requirement in electrical vehicles. So this is, now in Europe there is some project about multi-phase machines. So these are some applications. I will go faster because I have spent all my time. So this is some application, and BWM is trying to use five-phase machines. Even this 5-phase machine, 15-phase machines was used in 10 in Europe. So these are some application. Just to tell you something about the transformation now. Let's go to transformation. Yes, this one, not this one. This photo, yes, this photo is the machine designed in Gdańsk University. This one. Let's go. Yes, this is the transformation, the park transformation. You see here, with park transformation, we have 3x3 matrix. Here we have matrix by 5x5. And what is strange will be when we have this one. You see here, with n phase. And here we have two zeros. Each one will have a frame, and you see here what is the frequency: alpha, twice alpha, thrice alpha, because we can use it in English thrice, 3 times, but not thrice, 4th. Okay, and then we can go, so we can increase the frequency in each frame when we have transformation from the original phase, which is 5-phase, to sub frames. So we can have this to 0 is due if it is odd or even, the machine. With 5, we can have 1 0. With 6 phase, we can have 2 zeros. 2 components of 0. So this I will not talk because it's a problem. This is okay. I will stop here, and I will pass the speech to my colleagues. We will start from Professor Mokrani from Algeria, and then we pass to our colleagues from Poland. So, Professor Mokrani, are you with us? Professor Lakhdar?
Yes, I am with you.
So,
would you like me?
Yes. Would you like please to share your screen and your slides and start your speech?
Okay, thank you, Professor Abdullah.
Prepare your question. Don't worry. Yeah, don't worry. If I can answer to them, of course.
Is the slides shared with you, Professor Abdullah?
You can start now. Okay, you can start.
Yes. So, hello everyone. Assalamu alaikum. Many thanks to all of the attendees and to the conference staff for inviting me to participate in this interesting scientific event. My deepest gratitude to Professor Kuzu, Professor Guzensky, and Professor Moravich for their collaboration. So, I am Professor Mokrani Lakhdar, a teacher and researcher at the Electrical Engineering of Lagouat University in Algeria. In this second part of the workshop, I am going to speak to you about multi-phase inverters, topologies, control, and applications. Let us begin with the content of this part of the workshop. First of all, I will speak briefly about motivation to develop multi-phase inverters. Then I pass to the second part of the presentation concerning power electronics multi-phase inverters topologies. Next, I will present the third part of the presentation dedicated to the advanced power electronics multi-phase inverters topologies. Subsequently, I'm going to talk about the control strategies of power electronic multi-phase inverters. Later and finally, I will close the presentation by a set of applications of this kind of power electronics converters and conclude by a summary of some key points of the presentation. Foremost, I will present briefly my university, my research laboratory, and my research group activities. As I have said previously, I am from Algeria, a northern African country. My university is located in Lagouat city, 400 kilometers in the southern of Algiers, the capital of the country. Lagouat University comprises 10 faculties, among them the Faculty of Technology, that accounts for 5 departments, including my electrical engineering department, 6 research laboratories, among them my research laboratory, which is concerned with analysis and control of energy and electrical power systems. It is composed of 4 research groups. The first group works on modeling and monitoring power energy systems. The second, control and optimization of electrical power system. The third group concerns control energy management of electrical systems that I am leading. And the last group study automation of complex systems. Here are some research themes that we are working on in my group. Control and energy management of conventional and renewable energy systems, power quality fault management and active filtering of harmonics, identification and real-time tracking of electrical drives parameters, application of artificial intelligence and meta-heuristic optimization techniques to the control and identification of electrical drives and systems, computer-aided design of electrical machines, and finally, power electronics converters, modeling, and control. Let us now pass to the technical content of the presentation and talk briefly about the motivation to develop multi-phase inverters. Over time, the renewable energy systems become more and more powerful and competitive against fossil fuel systems. Moreover, the generalization of electric vehicles responds to several problems such as reduction of nuisance and sustainable development. So several applications such as these 2 applications are motivated researchers and industrial companies to develop more multi-phase drivers and or converters. The big challenge is to perform power electronics converters with high efficiency, high power, quality, low cost, and reduced weight and volume. So the motivations to develop multi-phase inverters are multiple. In fact, even most of electrical drives based on induction motors are 3-phase. Several motivations have led researchers to look at polyphase electrical drives, thanks to the redundant structure and reliability with fault-tolerant capability, as has been explained by Professor Kuzu. Moreover, phase number increasing becomes a more predominant factor to have additional degree of freedom. We have also the applications with low voltage and high current, such as electric vehicles, high power with high voltage and current that need for high switching frequency. Power quality improvement, electrical power split or segmentation, and the possibility to combine multi-phase with multi-level inverter topologies. Here are also other advantages of multi-phase structures. We have a reduced weight and volume, the possibility of fault-tolerant operation, We have also the possibility to generalize easily PWM carriers and hysteresis bank control with a simple phase shifting of control signals. We may also reduce the DC link current ripples and reduce harmonics, power losses, and filter size. In counterpart, these kind of converter structure and some of their control strategies, especially space vector pulse with modulation in particular, become more and more complex with phase number increasing. These kind of converters are more expensive, and in certain cases, we need several independent DC sources to supply this kind of converters. Let us now describe the different topologies of multi-phase inverters. Practically, a panoply of polyphase inverters has been developed in practice. One may classify this kind of converters into two big families: one, conventional multi-phase structures, and two, advanced multi-phase structures. The conventional topologies of these power electronic converters are a combination of standard modules with an equal subdivision of the current. Structures based on the well-known one-leg, two bidirectional switches. An integrated solution, such integrated solution may be smaller and widely distributed, and it needs a single DC source to be supplied. For the second family of advanced multi-phase structures with a panoply of variants, one can cite the structures based on neutral point clamped multi-level leg, flying capacity multi-level leg, cascaded multi-level H bridges, packed use cells topology, and Z source topology. We have also other topologies based on open-ended configurations, T-type topology, AC-AC, and AC-AC configurations. Let us review these different topologies. First of all, we have the structure based on a conventional one-leg two-level inverter. Here are the 2, 3, 5, and 9-phase two-level inverter schemes. It is obvious that we can mount multiple legs in parallel to mount any n-phase two-level inverter. For the advanced topologies, we have the structure based on a neutral point clamped multi-level leg inverter. Here are also 3, 4, and 5 levels NPC multi-level legs that can be used to build multi-phase multi-level inverters in the same way of precedent case. Same remark for the structure based on a flying capacity multi-level leg inverter. In fact, here are also the 3, 4, and 5 levels flying capacity multi-level legs that can be also used to build multi-phase multi-level inverters. In addition, one can use a cascaded full bridge single-phase inverters to build multi-phase multi-level inverters. But in this case, note that we need one independent DC source per H bridge. It is a real constraint, except in some applications, such as photovoltaic systems, where the electrical sources are naturally distributed and independent. Let us pass now to another topology, that is the packed use cells-based multi-phase inverters topology, that needs also one independent DC source per leg. Here are the schemes of a 4 in the left of a 4-level packed use cell inverter leg and a pack-based pentaphase 4-level inverter in the right side. In the same way, one can build multi-phase and multi-level packed use cells-based inverters. Elsewhere, Z-source inverters, different topologies, can be used to mount multi-phase multi-level inverters. Hereafter, for example, we give a Z-source multi-phase two-level inverter and a Z-source neutral point clamped-based M-phase inverter. Moreover, other topologies, such as flying capacity structure can combined with the Z-source topology to build up a multi-phase inverter. One can cite, for example, the Z-source flying capacity configuration and the Z-source cascaded H-bridge configuration, and so on. It exists still other structures of multi-phase inverters, such as open-ended configurations. Here are two examples of, first, an open-winding multi-phase converters with one DC voltage source, and an open-winding multi-phase converters with two DC voltage sources. One can find also multi-phase converters with multiple neutral points in the case of phase number multiple of 3, such as a 9-phase inverter with 3 neutral points and an n equal 3 by n phases inverter with multiple neutral points in general, the general configuration. In the same way, we have the T-type topology of inverters that can be used to carry out a multi-phase structure of DC-AC converters. Here is a T-type 3-phase 4-level inverter in the left side. One can easily multiply the number of phases arbitrarily. And here is also, in the right side, a T-type multi-level inverter input block that can be used to increase at will the number of output voltage levels of a T-type multi-phase inverter. Now, in some cases, an AC supply is made up by the use of AC-DC-AC converter. Here we are not speaking about inverters only, but the result is the same, an AC supply at the output with the controlled voltage and or frequency. So we can find, for example, one phase to multi-phase AC-DC-AC topology and 3-phase to multi-phase AC-DC-AC topology. Of course, here we assume that we only have single-phase or 3-phase AC sources at the input of the converter. Otherwise, one can speak about n-phase to m-phase AC-DC-AC converters. These configurations are bidirectional, and the power flow may be in the two senses. So far, I have terminated with the different topologies of multi-phase inverters. Let us pass now to the different control techniques of these kinds of specific power electronics converters that are summarized hereafter. First of all, we find the square wave control technique, which is rarely used in modern AC-DC converters, except some particular cases of very high power applications, where the switching frequency is very limited. And then we have the pure width modulation control techniques, which are diverse and include the bang-bang control technique, or current PWM, or hysteresis control. We have the Pwm Carrier Control technique, and we have the pre-calculated numerical PWM and the space vector modulation technique. Intuitively, we can deduce that all these techniques can be easily generalized to be applied to multi-phase inverters, except the SVM, space vector modulation technique, which needs a more complex and separate reflection. Right now, I'm going to review the different control techniques of multi-phase inverter. Let us take the example of a pentaphase configuration and begin with a 2-level leg-based inverter shown by the following figure. In the case of a square wave operation, here is the control chronogram in the left of the 10 transistors on one period. Note the 5th of period phase shift between any two consecutive legs transistors. The instantaneous voltages are expressed by the following formula in the bottom right of the slide. So one can use this chronogram and voltage equation to draw the line voltage curve. For the current PWM technique, hysteresis relays can be used to control the different phase currents of the pentaphase inverter in the same way as in a three-phase converter. The 5 sine wave signals to be compared to phase current might be a pentaphase equilibrated system. In this case, of course, here are the reference signals and control law. Now let us show some simulation results for the following data. Note the quasi-sinusoidal shape of the phase currents thanks to this PWM control technique, but the voltage THD is of about 40%. Fortunately, these harmonics, as it is shown in the spectrum of the voltage, are of high frequencies and may be easily mitigated by a passive filter that will be placed in the output of the converter. Let's go on with the Pwm Carrier Control. Here is a two-level pentaphase inverter with its control block scheme. One can note that the perfect similarity with a three-phase two-level conventional inverter, except the phase number, of course. Once more, the simulation results show the sinusoidal form of the output currents with convenient sheaf phase of a pentaphase system. However, the voltage harmonics distortion is still high. Note also that harmonics frequencies are multiples of switching frequencies, that is 5 kHz in this case, and may be easily filtered by a passive filter, which should be placed at the output of the inverter, as has been mentioned previously. Let us come back to the SVM PWM control technique. In this case, a pentaphase two-level inverter. We have 5 independent switch states that define 2 power 5, it means 32 cases, characterized by 30 output voltage active vectors and 2 passive vectors, as it is shown in the fundamental alpha beta frame and in the XY third harmonic frame. The calculation procedure of switching times of transistor for SVM of pentaphase inverters using, for example, 4 active vectors can be made in these 3 summarized steps. We use 4 active sectors to generate the needed output voltage vector, and one can choose small, medium, and or large vectors. Then we calculate the reference voltage alpha beta components in fundamental and third harmonic frames. And in the last step, we calculate the 4 switching times on a sampling period so that to generate the needed output voltage vector and nullify the third harmonic components, or inject a certain amount of the third harmonic voltage in some applications, such as in pentaphase electrical drives. Now we pass to the case of a 3-pack dual cells leg based pentaphase inverter illustrated by the following figure. Foremost, let us explain the principle of a 3-pack dual cells lag schematized by this figure. Note that we need 1 DC source and a capacitance between every 2 U cells. In this case, one can generate 4 voltage levels by a half cycle, as it is shown in the following Boolean operation table in the right side of the slide. So we can build voltages of 4 levels by a simple square wave control of the 6 switches of the packed dual cells leg. We pass now to the Pwm Carrier Control technique applied to 1 leg single phase inverter. We need 4 triangular carriers signals and the sinusoidal reference signals to pilot 1 leg of the packed dual cells inverter and generate the different states of the precedent slide Boolean operation table. Let us take the previous data again and redo the simulation in the case of a single phase 3-packed dual cells inverter. Here is the scheme of this inverter hooked up to a passive load. The following figures show the sinusoidal shape of the current. In this case, we have chosen the voltage of the source equal to the voltage of the capacitance is equal to the half of the DC source voltage, so that the output voltage has only 3 levels. Same remark for voltage harmonics, frequencies that are multiples of the switching frequency and may be easily filtered by the passive filter, as I have mentioned previously. We are going crescendo towards the pentaphase pack inverter. For this reason, let us pass foremost to the 3-phase configuration shown in this figure. Here are the control and the power subsystem of this inverter. Here is the power subsystem and the phase control subsystem. Here are some simulation results obtained with this data. One can note the multi-level voltage and the quasi-sinusoidal shape of the current, and a voltage THD of 28% with harmonics frequencies that are multiples of the switching frequencies of 5 kilohertz, which are filtered easily, as I have said it previously. Yeah. And now let us pass to a 3-pack based 5-legs inverter. It means a pentaphase inverter. This structure is obtained also by a simple copy and paste procedure of a 3-pack dual cells leg. The main drawback of this topology is that it needs 1 DC per leg. Here are the control and the power subsystem, yeah, and the part of the control subsystem. In the same way, we have simulated this topology supplying a passive load, and we have obtained the following results of voltage, current, and voltage spectrum and THD. This is the line-to-line voltage, the phase current, which is practically sinusoidal, and the line-to-line voltage with harmonics, with high order harmonics, high rank harmonics. And we have the phase voltage also with a THD of 20% and high order harmonics. Now let us pass to another topology of multi-phase inverters, namely the neutral point clamped multi-level leg based pentaphase inverters, and discuss again their control techniques. First of all, here is a single phase neutral point clamped 3-level inverter. The 3 levels of the output voltage are VDC, 0, and minus VDC, obtained respectively by switching on Q1, Q2, Q2, Q1, and Q1, Q2 respectively. To control the second leg of this single-phase full-bridge NPC inverter, one might use a second reference sine wave signal with a shift phase of 180 degrees. Here are some simulation results that show the output voltage and current of this converter in the case of a switching frequency of 3 kilohertz. We have done the same task of copy and paste to mount a 3-level NPC 3-level inverter. Here is its power circuit and its control block. The following simulation results were obtained for the same data. Here are the output voltage and current. Moreover, see the THD and the spectrum of the output voltage. Same remarks as I have mentioned previously. In the same way, we have built and simulated a 5-legs pentaphase NPC 3-level inverter as it is shown in this figure. Similarly, we have used 5 sine waves shifted by the 5th of period to elaborate the PWM control of this inverter. And here are the phase voltage and current. Moreover, the voltage spectrum and its THD that show the good filtering of low frequencies of these two quantities. That's all for the control techniques. Let us present briefly some applications of power electronics multi-phase inverters. We have low voltage, high current applications such as electric vehicles, aircrafts. We have also high power generation such as wind power, ship electric propulsion system with 15-phase induction motors and 15-phase converters also. By the end of this presentation, I would like to summarize some keynotes concerning this thematic of multi-phase inverters. First, the use of multi-phase inverters in industrial applications of low voltage and high current and high power with high voltage and high current is a trend. There is a panoply of variants and topologies of multi-phase inverters, more or less complex. In general, multi-phase power electronics converters are obtained by a certain redundancy of conventional single-phase or three-phase structures. Even the techniques can easily be deduced from those of classical converters, I mean control techniques, except the SVM, PWM, which become more and more difficult with the increasing of phase and power electronics switch number. I have just finished my presentation.
Thank you, Professor.
Thank you all so much for your interest and attention. Now I am fully ready to answer your questions and listen to your comments.
Okay,
perhaps after the by the end of
thank
the
you, Professor Mukrani. So we will pass to Professor Gizanski from Poland, from Gdańsk University of Technology in the north of Poland. So Professor Gizanski, Jaroslaw, yes, how are you? Okay, we cannot hear you. The mic, please.
Okay.
Yeah, okay, we can hear you now.
Now it's okay, I think.
No, yes. Please share your screen, the slides,
Yes.
and try to.
I will share.
Okay,
First of all, I would like to thank you very much for inviting me to attend the conference. It is very pleasant to me to be with you, with Professor Kuzu and Professor Lagdar and Professor Morawiec.
Professor Gizanski, please, yes. We limit the time to half an hour, okay? Thank you.
Okay. No. Thank you very much. Now I will share my screen, I hope. Do you see my screen? Professor Kuzu?
Yes, we can hear you, yes. You can start.
So, I'm Jarosław Guziński from Gdańsk University of Technology. The next speaker, Professor Morawiec, is with the same university. Our university is in Poland, in north of Poland. Now we have 8 faculties. So I am from Faculty of Electrical and Control Engineering. At the faculty we have 9 departments, and my department is Department of Electric Drives and Energy Conversion. We have more or less 100 academic lectures and more than 1,000 students. My department is specially oriented into the electric drives and power electronics. The main subjects we are working are control of electrical machines, especially sensorless control of electrical drives, without any speed or torque sensors. We are also working with diagnostic of electric drives and power converters. And regarding the subject of our workshop, we started to work with 5-phase drives. I think that's more or less 10 years ago. During that time, we have designed few, I think that's more than 10 motors, and we have built in 5-phase inverters and designed new or implemented new control methods for inverter part as well for motor part control. Some of our drives have been presented under exhibitions, and now we are still working with that subject. Generally, we have started with induction motors. Now we are doing some research on 5-phase brushless DC motors and 5-phase permanent magnet motors. The subject I would like to shortly present you is divided into two subjects, the inverter control and the motor control. The first subject was very good presented by Professor Lagdar. Now I will present only some subject related to our research at the department. Control of 5-phase induction motor drive is divided into the two subjects. Why? Because in a drive we have two parts, the power parts, which consist of the converter, for example, voltage inverter, and the 5-phase motor, and the control part, which is divided into generally two subsystems, PWM control, so the methods of controlling the transistors inside the inverter, and the superior system for controlling some variables related to the motor as speed, torque, flux, motor current. Additionally, we need some estimation systems in the drive for estimating some variables which are not easy to measure, or the price of the sensors or the way to install the sensors is not easy to implement in the industry. That part, variable estimation, that problem will be presented by the next speaker, by Professor Moravec. Here is also some additional part which is not usual in all drives. It is the low-pass filter, which is installed in some drives to protect the motor against the bearing currents or to improve the motor efficiency due to the better quality of the supply voltage and current waveforms. So in the 5-phase inverter, we have 10 switches. The combination of that switches is equal to 32 possibility, which is divided between 30 active vectors and 2 passive vectors. 30 active vectors means this is the state that the output voltage of the inverter is not 0, and 2 passive vectors, it means that the output voltage is equal 0. So we have that possibility, 32 states, for generating the inverter output voltage. And how to do that? Generally, we can divide the inverter control method into a few. First, the methods which are not using PWM. This is the 10-step mode of operation. The use of that control is limited into some particular states of the drive operation. And the next group of the inverter control, it is generally group of PWM control. And between that methods, we can find sinusoidal-based PWM and some solutions for space vector modulation. Here I have listed only 2 of them because we are using that methods in our laboratory. You can find also in the literature many of the methods as Professor Lagdar presented. 10-step mode of operation, it is very simple control. In that control method, each of the transistors in the inverter is switched on during half period of the output voltage. There is only the possibility to influence on the frequency of the output voltage of the inverter. The possibility to change the output voltage is limited, so rather that method could work together with the controlled rectifier. However, that state of operation is used in case of very high speed of the drive, where the output voltage is set to the maximal value. In case of using the PWM, it means that we are going to the overmodulation range. The quality of the current for that kind of the output voltage, rectangular output voltage, is very low, but it is only the possible method for the which is used for the high-speed motor operation. To improve the quality of the output current, we can use some of the PWM control of the inverter. For example, sinusoidal-based PWM, where in the control system we are comparing the high switching frequency carrier signal with a modulation signal. And the modulation signal, this is the reference signal with the desired voltage level and the desired output frequency of the inverter. It is easy to understand control of the inverter using the idea of sinusoidal-based PWM. However, in most of the inverters, the space vector modulations are used. The method of space vector modulation is based on the some relation between the vectors. Vectors are representing state of the switches in the inverter, because we have 32 possibility of switching the transistors. We also have 32 vectors. Here there are two planes which are related to the degree of the freedom in five-phase inverter, because in a five-phase inverter we have two planes. We can control the output voltage, and that planes are related to the first harmonic voltage and current and the third harmonic voltage and current. So by controlling, switching to the different vectors in that method, we can influence on the first and third harmonic of the inverter output voltage. We can do that in a controlled or uncontrolled way. Generally, if we are thinking about the inverter control, we are thinking about the first harmonic control only, and the third harmonic we would like to neglect. But using the five-phase motors, we have the additional degree of freedom. Using the third harmonic variables, we can influence on the motor operation to obtain the better results regarding the output torque. If we are controlling only the first harmonic without any additional special control for the third harmonic voltage, we can observe the third harmonic in the motor, which are not required, because if that third harmonic is controlled or not controlled at all, it can influence on the increasing of motor losses. Here we can, I presented the currents in that two planes, the first harmonic plane and the third harmonic plane. We can see that that first harmonic is controlled value. The third harmonic is not controlled. There is a very high peak of the third harmonic current. Why? Because it is a method used for supplying the five-phase induction motor with distributed windings. So for that kind of the motor, the model of the motor for each planes, first and third harmonic, is like that. The first harmonic is, as we know, but third harmonic model is limited only to the stator resistance and the stator leakage inductance, and that reactance is very small. So if we apply any of the third harmonic voltage, here the current which flows in that second plane has a very big value. So the total current of the motor will be distorted, and the losses in the motor will have a very big value. So to solve that problem, we should to implement the different methods of space vector modulation. For example, neglecting the third harmonic. Is it possible to use some trigonometric relation between the vector? For example, here, if we look at the reference voltage vector, we would like to produce on the inverter output, we can construct that vector using, for example, 4 active vectors from the same sector, and we can find some values of that vectors, which if are selected properly will give us the 0 output voltage in the second plane. So if that method is implemented, we can observe that the third harmonic currents are set to 0. So no losses, no additional losses will be in the inside the motor. But in some kind of the induction 5-phase induction motor, there is a possibility to produce additional motor torque, to increase the motor torque. The construction of the windings should be different, like in the classical induction motor, so that the windings of the stator should be concentrated. In that case, it's possible to add additional component of the rotor flux, the third harmonic rotor flux, which should be synchronized with the first harmonic rotor flux, so the resulting rotor flux distribution could be close to the trapezoidal shape. Why that resulting rotor flux is interested for us? Because of that, we can better use the magnetic circuit of the motor. Here, that maximal value for the first harmonic is in the usual motor is set to the value which is close to maximal value of the flux, and that maximal value of the flux is limited to the small part of the stator circuit, and using that additional flux harmonics, we can increase that maximal value of the resulting flux to the same value, and so the magnetic circuit of the stator will be used better, not only for the short size, but for a greater size. And how, as the results which are presented in the literature showing us, is it possible, generally it's possible to increase the motor torque in a 5-phase motor up to 15% in comparison to the 3-phase motor with of the same size. To do that, we have to use the PWM algorithm where there is a possibility to control the third harmonic voltage. The third harmonic voltage. So with that, generally we can compare the 5-phase motor as two motors working on the same shaft, and one motor, this is the big motor, supplying with the first harmonic voltage and current, and there is an additional small motor which is generating additional torque, and that small motor is supplied with the third harmonic voltages and current. For a motor with a concentrated windings, the model of that motor is nearly the same for the first harmonic circuit and the third harmonic circuit. The difference is only with the parameters which are here. And because of that model, we can see that there is a possibility for generating the additional torque. For example, using the PWM with 6 active vectors give us the possibility for controlling the third harmonic fundamental. And if we see at the output voltage of the inverter, we can observe the waveforms like that. There is a little different if we compare with a 3-phase inverter, because in the 3-phase inverter, the supply current of the motor is sinusoidal. Here, in the 5-phase, inverter, the supply current will be could be trapezoidal or triangular, depending on the motor load. It is a result of the additional flux component we are generating. Generating inside the motor. We can observe that for that current there is a first harmonic value and the third harmonic value of the current. Now I will go to the upper part of the control. There is because there is we have the PWM control and the motor control variables, and all of the methods which you know for 3-phase motor control, we can implement to the multi-phase motor control. So, for example, field-oriented control, direct torque control, model predictive control, or nonlinear control, or any other. But we have to think about that in the 5-phase motor we have additional degree of freedom. We have a third harmonic plane of variables, and if we omit that third harmonic variables and we are using the PWM, which is where the third harmonic voltage is set to 0. We have the same control as in three-phase drive. For example, here there is a control system, field-oriented control system for 5-phase induction motor, and there is a control subsystem only for the first harmonic variables, and the PWM, which is used here, this is the PWM which is working in that way that third harmonic of the output voltage is set to 0. So nothing different if we compare that structure with a three-phase system. But here the only benefit of using the 5-phase motor is the possibility to work without one or two-phase supply. No any additional torque will appear in that system. However, if we used a 5-phase induction motor with concentrated windings, there is a possibility to add additional control systems. For example, here, there is a possibility. This is a field-oriented control, which is divided into two subsystems: the controlling of the first harmonic variables and third harmonic variables. The third harmonics set torque component of the current, and the flux component of the current is set to the 15% of the first harmonic set values. So I hope if the system works well and that harmonics are synchronized well, the output torque is increased. There is a possibility which we are using in our research, the possibility of controlling the good controlling of the drive using nonlinear control, and here we can see the structure used for controlling the motor. We see that is more complicated than if we compare with the three-phase drive. For three-phase drive, only the upper part is used, and for 5-phase drive, if we want to generate the higher torque, we have to multiply the flux and current controllers. So 4 additional controllers and additional controller which is used to synchronize the first and the third harmonic flux. And with using that control system, the motor torque is increased here for the same current limitation set to nominal value. Here, the black line, we can observe that without that bottom part, the third harmonic part control, the torque is limited into the 0.85 in per unit. Here, if we switch on that additional control part and synchronize well the first and third harmonic flux, the motor torque has been increased into 0.94 per unit. In per unit 0.7, I think it means in that case nominal torque. We can observe the good result if we observe the speed acceleration. Here the speed acceleration is finished here, and there is a faster speed acceleration using that additional torque. And the current in both cases is the same. Maybe at the end I will present some photos of the research test bench. Here is the drive. We are using one of the test bench we are using for research. On the left side, this is a three-phase induction generator, and on the right side, it is the five-phase induction motor. Both of them are looking the same because that five-phase motor was converted from three-phase. So outside it looks like the same, but difference is in the stator. We are designed and mounted here the newer stator with a newer connection of the stator coils. For that, to supplying that five-phase motor, we have used the five-phase inverter, which was done in the lab, controlled by DSP processor. This is the control part. On the right side, there is a power part with a 5 legs of the inverter and additional leg for braking the motor. And the results which are presented here are from experimental system. For example, for speed reverse, we can observe that the speed is following the reference signal even for a very low speed reverse. And I think I will finish now. Yeah. Thank you very much.
Okay, can you make the first slide? I want to show the people the first slide of your presentation.
Yes.
The first slide. Yes, here. No, the other with the photos of the exhibition in Germany.
Ah, yes. Ah, here.
Yeah, yes, this one. Just to tell people here, you see Angela Merkel there. They have this team win the competition for implementation of the control drive of this machine. This was Merkel is there, and the system is there. So the team from Gdańsk University win this competition. Just to mention it.
Here,
yeah.
For the exhibition, that stand was prepared by our department in cooperation with one of the Polish company.
So we go to Professor Moravich. Professor Moravich.
Yes.
Yes. Can you share your screen, please? And we are limited by time, so try to minimize your time because.
Yes, Professor Kozu, I cannot share my presentation because I haven't permission. Please give me permission because I. Oh, okay. Thank you.
Yeah.
Okay.
Yes.
Yes, it's okay?
Yeah, yes.
Yes.
Okay, it's okay. You can start. Just please
Okay.
try to make it in 25 minutes if it is possible, because we need some few time for the questions.
Okay, I try to do this.
Yeah, it's difficult. But
Good morning. Good morning. My name is Marcin Morawiec, and I would like to present a speed observer structure for multi-phase, five-phase machines. It will be short review of the estimation method which can be used in the sensorless control of the multi-phase machine. In the literature, there are the different speed estimation methods of the induction motor, which can be applied to multi-phase motors, of course. We have three main groups of estimators: physical, algorithmics, and neural network methods. And the large one group is algorithmic methods, and state observers, nonlinear observers, extended observers, non-stationary, linear, adaptive full order observer, sliding mode observers, and estimators can be divided to subgroup estimators with the speed calculator algebraically, and estimator which use the techniques of adaptive system, and where are the MRASes, large MRASes approaches. And of course, Kalman filter and neural modeling on the training online or offline. And the most popular approaches are based on the full order or reduced state observers presented by Luenberg in his thesis in '63. This is, of course, state observer without the estimation of rotor speed value. However, this approach was extended to the estimation mechanism and proposed in '90 by Kubota. The other solution is based on a model reference adaptive system, and was proposed by Tamai in '87. This is the large groups of the structures of the observers. And Krzemiński proposed the nonlinear adaptive estimation of the rotor speed value in '99. All this approach can be used in the sensorless control of the five-phase multi-phase machines. In multi-phase machines, there are different references planes. In each of them, the observer structures should be applied. And the sensorless system means that the system in which the rotor speed is not measured but estimated by observers. And one of the estimation method is the model reference adaptive system, MRAS. The basic form of MRAS is based on voltage model of the machine and current model of the machine. In voltage model, we use the stator flux differential equation, and the rotor flux components are obtained from algebraic equation. And in the current model, we have the rotor flux differential equations for the estimation of rotor flux components. And the rotor speed value is estimated by using the integration of the error of or proportional integrator PI controller. We have the rotor flux components from different machine model, from voltage and from current. So these components are compared, and in this slide the scheme of the model reference adaptive system is presented. The estimation rotor speed value can be obtained by using PI controller and the tuner adjustable model is the current model of the machine, and this speed is as treated as input to this current model. However, the properties of this solution is not good, especially for the low speed range. Therefore, the better is use the extended form of MRAS, which is named MRAS CC in the literature. This structure was proposed in these papers. MRAS CC is based on the rotor flux differential equations. It was named by current simulator and stator current estimator, stator current differential equations. The rotor speed value can be obtained by using PI controllers, and this error. And MRAS CC is more stable for the low range of rotor speed than classical form of MRAS presented previous. However, the problem with the stability still doesn't overcome. The most popular solutions in the literature are the state observers, like Lowenberger and Kubota. This structure is, of course, stable. It's based on mathematical model of the machine, and it's stable if this tuning gains, key I and key F, 1 and 2, are higher than 0. In general form, the eigenvalues of the matrix A minus LC can be chosen arbitrarily by appropriate choice of the observer gain L. So the poles should possess negative values when the structure is stable. And the rotor speed value can be estimated by using the value of this arrow. This is the cross product here of the rotor flux and error of stator current vector components. And of course, this expression is derived on basis on the second Lyapunov method. On this slide, the scheme for the speed estimation is presented. The rotor speed value is estimated by classical PI controllers, and the observer structure is adjustable by this value. So this output is adds to this observer structure. The question is, what are the main problems with the speed observers? This problem we can divide into main 3. Small accuracy of the estimated rotor speed value due to, for example, the measurements of the stator current or different noises in the system. A lack of robustness on the uncertainties of the machine parameters. The structure can be unrobust on the nominal parameters changing during the machine work. And the lack of stability in the different working points close to 0 speed and regenerating mode. This is a well-known problem of the speed observers, structures. The first two can be overcome if we, for example, take the different solutions, other observer structures with, for example, sliding mode approach. The third can be overcome if to the observer structure will be applied the update control law. So additional feedback will be introduced to the observer structure. And these improvements are proposed in this paper by me, and these improvements are based on the adaptive full order observer, and the observer structure is based on mathematical model of the induction machine in which the nominal machine parameters are defined from A1 to 6. TL means load torque of machine, and J is inertia. And the AFOS adaptive load observer, AFOS speed observer structure has two differential equations for the stator current components in alpha beta reference system, and two differential equations for rotor flux vector components. And the stabilizing functions are introduced here, and V alpha, V beta to these currents equations, and V psi alpha, V psi beta to rotor flux equations. The stabilizing functions are introduced to stabilize the observed structure and will be obtained by using the Lyapunov theorems. In the first stage to design is to provide the stability analysis of using the Lyapunov functions, theorems. We can define the errors in the observer system as follows. This is the rotor speed error, rotor flux components error, estimated stator currents and components error. And based on these errors, it is possible to determine the form of the Lyapunov function. Of course, this Lyapunov function should be positive defined, and the derivative of the Lyapunov function has the following form. Using defined previous estimation errors and substituting the mathematical model of the proposed observer structure, the model of the speed observer's estimation errors can be following determined. And the observer structure will be asymptotically stable if the derivative of Lyapunov function is negative determinant. So the introduced stabilizing function can be obtained from this condition. I choose this stabilizing function in following form, and value of the rotor speed can be adaptively estimated from classical adaptation law. Yeah, this is a classical solution. The observer structure is adjustable by using the value of this rotor speed, and has the problem that for the low speed range, as well as for regenerating the machine mode. To improve the speed estimation, it is possible to propose to introduce the term which is the error of estimated rotor speed value here multiplied by gamma coefficient. This is tuning gain, of course. However, this is the error of rotor speed, and in the sensorless operation, the rotor speed is not measured. Therefore, the additional signal, which is named S omega here, is added instead of this error of rotor speed estimation. And this signal means the scalar product of the two vector stator current error and rotor flux vector. Of course, here we have cross product, and value of this additional feedback is increasing for different machine working points, especially in the regenerating mode of the machine. For perpendicular vectors, this value is equal to 0. So this is only ideal case. And the other approach is the non-adaptive speed estimation, in the adaptive full order observer. But the question is if it's possible to estimate the rotor speed by using non-adaptive equation. In adaptive equations, adaptive law of estimation of rotor speed, there are two parts. First part and the second part. And for the steady state, following equality holds. Yeah, we have proportion. We can assume that these errors, stator errors estimations, are proportional to these terms. So multiply by a rotor flux component here, and transforming, it is possible to obtain the rotor speed dependence in the algebraic form. The rotor speed can be estimated by this algebraic dependence. However, this is only the cross product, like this adaptive law of estimation. Therefore, I notice that the value of the estimated speed is not satisfactory because it's only cross product of these two vectors. So the same problem exists as in the classical adaptation law. But it is possible to rewrite from this equation following dependencies. This is the cross product from these equations, and this is the scalar product, which is for ideal case is equal to zero. So if we sum this both together, we can obtain and simplify. We can obtain the new form for the non-adaptive rotor speed estimations, in which this S omega functions is included. And now I'd like to show the simulation results with the proposed improvements. We have the regenerating motor mode of the machine and regenerating mode of the machine. These are the estimated rotor speed presented, rotor speed error, filtrated S omega signals, so this is a scalar product. Stator current components error, alpha, and electromagnetic torque. The rotor speed is estimated by non-adaptive scheme. And we have two cases. This is the machine is reversing from 0.1 to minus 0.1. And this is the motoring case. And here is a regenerating mode of the machine. For two cases when Kc is equal to 0, so we have no this additional elements, this scalar product of this vector, and in this case Kc is different to 0. So however, for Kc equal to 0, the estimated value of electromagnetic torque is almost the same like value of the load torque. This means that the vectors are perpendicular, and the value of S omega, this value, is very close to the 0. So we can say that the rotor speed error is almost 0. This is visible in this figure B. And Kc is 2, 5, 8, 12, and 15. So the rotor speed is very accurate estimated. And in this slide, these are the experimental results. The estimated rotor speed, electromagnetic torque, square of rotor flux vector, and square of stator current vector. the rotor speed error are presented. The same case like previous motor mode and regenerating mode. For KC higher than 0, we have good properties of the variables of the sensorized control, and for KC equal to 0, the speed observer is unstable, what is visible here, and of course the inverter was turned off. And in this slide, this is the same regenerating mode of the machine and the comparison between two adaptation control to scheme of the speed estimation, adaptive speed estimation and non-adaptive speed estimation. Here is the, after 1 second is the rotor load torque is turned on. In this case, the rotor speed is about very small, and about 71 RPM. Let's go back to the 5-phase machines. The sensorized control of the 5-phase induction machine is presented in the slide. We have dual observers for the first system planes and for the second system planes. The rotor speed for the second system planes is 3 times more than in the first system plane. Both the system plane must be synchronized together by using, for example, the rotor flux components. And of course, I use here on the big stepping controller and Z transformations. Reference value are at here. These are the rotor speed value for in the first system plane and the rotor reference square of rotor flux in the first system plane and for the second system plane. And in the control system, I propose the input-output linearization, which was named in literature by Z transformation and has the following form. So using the machine state variables, we can obtain the transformation in following form. Z5 variables has no influence on the system. This is additional variables. And index E means E1 means first system plane, E2 means the second system plane. And to find the controller structure, I use the backstepping. So this is the feedback control via backstepping presented in my papers, and the control variables can be obtained and determined as follows. And now I would like to present you the experimental results. In this slide, the 5-phase 5.5 kilowatts machine is starting to nominal speed. So this means 1 0 in per unit value. And the machine on the right side, machine is reversing to the nominal value. And the estimated rotor speed, electromagnetic torque, square of rotor flux, additional variables Z4, estimated load torque, and stator current vector for the first system plane and for the second system plane are presented here. The estimated speed very smoothly passes through the 0 rotor speed in this figure. And in the next slide, the machine is starting to do nominal value. In figure A, the machine, the following variables are presented. Estimated stator current for the second system plane, estimated rotor flux vector components in the second system plane, estimated rotor flux vector components for the first system plane, and rotor speed in the second system plane. The sum of the rotor flux components alpha in this is the sum of for the first system plans and the second system plans. This is shape is trapezoidal. On the right side, in figure B, the machine is loaded about 0.7 in per unit load torque after 200 milliseconds, and load torque was turned off after 1500 milliseconds. And the variables which are named Z are presented, and estimated load torque value and stator current components for the first and the second system plane. And in this slide, the very low speed reversing about 7.2 RPM in figure A for the backstepping controller is presented. These are the estimated rotor speed synchronization error of the two system planes, stator error recurrence ESD, for this in the first system plane, stator current ESQ in the first system plane, and stator currents components for D and Q for the second system plane. This is the backstepping controller base control, and on the right side we have the field-oriented control with 4 PI controllers. This is only speed about 15 RPM for field control, because the error was very large here in this case, error of synchronization. So we can say that backstepping control with the state feedback control is more effective than Ford's field controller. The synchronization error in this case is very small. It's very small, in the case of it's almost zero here. And the conclusion, the classical speed observer structure can be implemented in the sensorless control of the 5-phase machines. A different speed observer approach can be implemented. To improve the robustness of the speed observer structure, the additional stability function should be introduced. The sensorless control system is stable for the regenerating mode of the machine and for the rotor speed smaller than 0.01, about 7 RPM. The estimation error of the rotor speed is smaller than 0.01 in per unit, so it means about smaller than 1% or smaller in the stationary state of the machine. So thank you very much for your attention.
Thank you, Professor Moravich, for this presentation, and also we thank all our Professor Kuzu, Professor Gdansk, Professor Mokrani Lakhdar, from Gdansk, from Poland, and from Algeria. So I think the assistants have a lot of questions. Okay.
Assalamu alaikum. This is Bassam from the maintenance management. I would thank you for all the speakers for the wonderful presentations and interesting subjects. It is really a revolution in the electrical machines and the drives. Actually, my question is in the generation or in one application, in type of application, that is the smart grid. My question, especially the grid-side inverters, The question is, what about the flexibility of the control? Is there any topologies in that with the acceptable harmonics for the smart grids?
Maybe the question is not clear, the colleagues with me, because we are talking about, you mean that for the generation with 5-phase generator?
5-phase generator.
Yeah. Actually, just to mention this is important because in the wind turbine we are going to use this kind of machines, and now this kind of machines are used as generator in the propulsion machines because the ships, when they are in the sea, this is a great problem, and we need to have some reliability, and that the machines must must have some continuous operation mode. So these machines now are actually used in the ships, in the propulsion systems as generator, you know, that in this case. Also in the wind energy, maybe there are some application right now, and we are going to use these machines as generator, and we have more reliability than the 3-phase machines. I'm talking about the synchronous 5-phase machines because it can be considered as generator. Also the induction generator, we can also have the induction generators, and it has more reliability when used with wind turbine. So this is 2 cases that we are focusing on it. And if we are talking about smart grid is something very large, and we can use this, we can use other things, but our options, our suggestion for the industry to go for this kind of machines. The controllability now is available. Everything is available. Even we are talking about the observers, which was a challenge for this domain of research. But now everything is ready, and I think we can use this kind of machines in generation and also in driving. So also in smart grid, it can have some applications when we are talking about the side of generation.
Well, good afternoon. My name is Abdul Malik. I'm a renewable energy engineer student. I was wondering about the feasibility of adding the multiple phase into airplanes, and will it make it safer to use, and will it increase the weight? That's the first question. The second question, will multi-phase engines will replace gearbox, and if it does, will it increase the efficiency and reduce the maintenance?
Professor Gzynski, Professor Mokrani, Professor Moravich, I will answer to the questions, of course, but if you wanted to answer, you can just ask me, okay? Professor Gzynski.
Okay.
Do you want to answer to this question?
Yes, I can
yes, you
answer. Generally, I think that multi-phase motors are used in the airplane industry. I think that rather 6-phase motors. And regarding the possibility of using 5-phase motors and the size of the motors, is it possible to obtain a smaller size of the machine due to the higher torque generation using the third harmonics of the flux? How much? What will be the size of the new motor? It is not easy to say. Because the possibility of increasing the torque depends strongly on the design of the magnetic path of the motor. but I think it's possible, and probably will apply that model to some special applications.
Yeah, exactly. Now, people who are working in this domain, also, as I have mentioned in my presentation, maybe in the satellite, we will use this kind of machines because they are more reliable than three-phase machines. Also, we can use this kind of machine in the airplane or other places. It will be good. The other point, when we change in the terminals, the power in the terminals of the winding, we can have change the speed without need to gearbox. This is the application of the electrical. When you are talking about, I think the reliability of water. Yes, they are more reliable, and the maintenance, we have less maintenance, and we have to do the maintenance. We have to do the maintenance. Some processes need to make the maintenance. Some process needs to be continuous in their operation without interruption, because we will have a lot of losses there, money and equipment. So when we use five-phase machine, we have time to make the maintenance without making the interruption of the operation of the mode of the process. In industry, I'm talking about industrial application. This is very important. Also, another point, we have the density of torque. When we are talking about the torque to the volume, this is important. Five-phase machine is better than three-phase machines. Professor Moravich, Professor Lakhdar, if you have something to add.
Maybe if I can add, yes. Yeah. Regarding the drives without the gear, the theory of using multi-phase machines as a machine with a switchable number of poles is in theory. I'm afraid that there is in real systems there is no such good results as in theory. We are working with that subject, and we are investigating the drives with a switchable number of poles, but still now we don't have yet good results.
Professor Kuzu.
Yeah.
Professor Kuzu.
Yeah,
Professor Kuzu.
Yeah.
Professor Ahmed, I would like to add something about this question.
Okay, you can.
Yes, thank you. If we have multi-phase motors with a multiple number of free, in this case, we can build supply from conventional supply, three-phase supply, for example, using some special transformers. And in this case, we can, as has been explained by Professor Kuzu, control the machine in order to modify its phase number, poles. But in the case of pentaphase machines and multi-phase machines in general, we have not conventional supplies that can supply the machine, and we have to use electronic variators to control the speed. And in this case, we have not to I think that the the gearbox can be eliminated, since we have the control of the speed in a large range by the use of electronic power converters.
Sure.
Thank you.
Okay.
Assalamu alaikum. My question regarding the multi-phase induction motor. You mentioned that in the case of phase loss, the multi-phase induction motor will continue running normally. If one phase lost, or two phases, but should not be for example, A and B. If A and B are lost, it will stop. This of course, this is a common problem, operational problem, but there is another common operational problem, which is the unbalanced voltage. So is there, since you have multi-phases, so if there is unbalanced voltage, you are not losing the phase, but there is no balance that will be reflected on the current. There will be unbalanced currents. Is the problem will be okay, or it's the same with the three-phase motor?
Thank you, Professor, for question.
This is very good question. Because when we are talking about three-phase machine, you know we have three components in case of imbalance. One is direct or positive, one is negative and the inverse, and the homopolar or zero sequence. What happened with, for example, five-phase machine? We will have five components. So we will have more problems, two in one direction and two other in other direction. 7, we have 6, and so on. So we have other components, but it remains the same. It remains the same, and the efficiency it depends of if you have to, because you have mentioned it will operate normally. No, it will not operate normally, but it can operate with less power, with less torque, but it can continue its operation without interruption, but it cannot work normally, as I have mentioned with the current. There is some fluctuation in the. When we lose 2 phases, but not sequence phases, so we have the same problem. So with the imbalance, we have the same problem, like 3-phase machines, but with 5-phase machines, we have 5 components, and we can make the control more reliable. The other interesting thing, maybe I'll ask question, my colleagues also to answer this question. There is a possibility for 5-phase machine to connect 2 machines in series and to control them with 1 inverter. This is a very good operation, because when we have the permutation, we can have the permutation from the other side, and we can series. Atif Iqbal is a professor from Qatar University, so he has done his PhD with Emil Levy in Liverpool in 2016 about this kind of machines. So we can make 2 5-phase machines in series, controlled with 1 inverter, of course, 5-phase inverter. So Gizensky or Mokrani or Moravsky, if you have something to add.
I can add.
Yeah.
Yes. There is if I confirm, there is a possibility, very interesting possibility to control independently 2 motors supplying from the 1 inverter, 5-phase inverter. Even if the motor are supplied parallelly connected or in series connected, our PhD students are one of our PhD students is working with that subject, so probably we can show results soon.
Thank you.
Thank you very much. I just have, I don't know whether it's a question or a remark. Most of the commercial airlines that I knew of operate on about 400 hertz. So how would like a 5-phase machine deals with that, or that would be addressed through rectifiers? I mean, how will they work in that environment of the neighborhood of 400 hertz?
Okay, thank you for this question.
Yeah, sure. The first thing, that when we are talking powering the 5-phase machines, so it will be powered by inverters, means that's a conversion system. So from the input side, will be a rectifier, then it will be a breaking system, then the inverter. There's another option. We can go directly from AC to AC by matrix converter. So we can go matrix converter. The input is 3, and the output we can get the number of phases as much as we want. So we can make directly the control from the input. The problem that with this kind of converter, we will have some harmonics in the input side. And this will be a problem because we will make some pollution for the source. That from where we are powering. Also for the rectifier, we can get this. But fortunately, with the new technology, for example, with the pulse width modulation rectifier, we can avoid these problems and minimize the harmonics from the other side. So I think it doesn't matter from the input side, what is it? As we have the power, with power electronics to make the conversion as we want. Gizensky, Lakhdar, do you have something to add? Moravich?
Yes, Professor Abdullah, yes. As you have said, we can use AC, DC, AC converters, which are called also back-to-back converters. In the AC side, we have, as you have said, a PWM rectifier, which can absorb sinusoidal current and avoid the pollution of the source by harmonics. And in the right side, I mean in the load side, we have to use
Professor Gizensky, do you have something to add?
Yes, regarding the frequencies, supply frequency, it doesn't matter, is it a 3-phase or 5-phase motor. Generally 400 hertz could be applied. If we want to supply with a higher frequency, for example, for a very fast motor speed, we have only to use the properly designed magnetic path. I know that the Professor Morawiec now is working in the project where the very high-speed 5-phase motors will be designed and built. I think that is 30,000 RPM probably motors. So I hope that he will obtain interesting results with that high-speed 5-phase motors. So. Thank you.
So we can think that I have mentioned in my presentation.
Sorry for the interruption.
Yeah, we are talking about the flux weakening.
I have a problem with the network.
Without weakening flux, because as I have mentioned, when we want to enlarge the speed, we have this case. We can send the connection, the terminals on the machines. And also when we are working with the low speed, also we have, but I think that for 5-phase machine, it will be better. But to control the speed, we have the power to control speed as we have the power electronics.
Sure. So, we have another question. Okay, so thank you very much for this workshop, and we close the session. Thank you.
Thank you very much.
Thank you.
It's okay.